I'm Thomas Hall, Executive Director of CleanStart, and welcome to our perspectives with T Omega. I'd like to welcome Brita Formato, who's an executive with over 25 years of experience in the energy industry. She has worked in shipping operations, strategies, mergers and acquisitions, risk management, corporate finance, renewables, startups across the oil, gas, electrical utilities, and offshore wind organizations. She has a great track record of working here across multiple geographies, organizations, functions. She's now the chief executive at T Omega and leads the company's strategy, operations, and development of floating offshore wind. And one thing else that I find cool about her background is at Duke Energy. She worked with their business ventures in electric vehicles. So if you ever want to learn about what's happening at Duke Energy, she's also a great person to ask. So with that, I'm actually going to stop sharing my screen and welcome Brita to share.
Thank you, and Happy New Year, and thank you for the introduction, Thomas. I'm really, really excited about talking to you about the opportunities and for offshore wind in California, and also specifically about T Omega Wind. I will try to share my screen as well. Let's see if I can get that back up on the screen. Can you see my screen?
Yes.
Yes. So thank you for this opportunity. So at T Omega Wind, we are radically redefining what is possible for the offshore floating wind industry. So our mission is really to democratize offshore wind. The wind resources in the US are really vast, right? And they could able to meet the power demand, the offshore wind power demand in the US by several times over. So just like the globally, majority of the offshore wind resources are in over deep waters. So, and that's the same thing. I think I need to just say, got it on that. Yeah, thanks. It's and in California as well is over very deep water, and that will require floating solutions really to be able to harvest those. So today, though, only less than 0.5% of all the offshore wind generation is floating. So it's really at an early stage, the offshore wind industry. And really the key to the energy transition and including the offshore floating wind in that is really, we need more innovation in with the technology, and we need to lower the costs. And if you compare our technologies to the legacy technologies, we have lower production and installation costs, as well as we can really go anywhere where the other solutions can go, but also in other areas where they're not viable. So I want to start with, let's see if I can get to the next slide. Yeah, with our story. So we are headquartered in Boston, Massachusetts, and we were founded in 2018 by Andy Myers and Jim Papadopoulos. They met over 13 years ago as professors at Northeastern University, and they became fast friends as they both had a really big interest in offshore wind. And while Andy was on a sabbatical with the Department of Wind at the Danish Technical University in Denmark, he and Jim came up with his manufacturing floating wind turbine concept that avoided many of the limitations of the existing land style designs. And they really started with, we say blank piece of paper, but with the radically redesigning of the floating offshore wind turbine from the, as we say, from the water up. So let me just, it was a great introduction, Thomas. So you covered most of what I have on this slide. But so I was born in Oslo, Norway, and that's where I grew up with a really passion for the outdoors and appreciation for the fragile Arctic nature. And I had a passion for sailing. I grew up sailing competitively on the Oslo Fjord, and I did that through college in the United States too. So I know the oceans, I know the possibilities and opportunities to harvest the wind. And you covered this very well. So the companies that I worked for and that I worked for in the EV industry, I want to also mention that I did M&A work in 2008. I worked on the acquisition of the company's first major renewable resources. That was a portfolio of onshore wind assets. So just to cover our entire management team here, we talked about the three first of us here, and we have Vin Mosiano, who's our Chief Operating Officer. He is a serial entrepreneur who has started several companies. Among them is Halo, and that is a micro wind turbine company. And he's also an engineer and a patent attorney. And then Dave, who's also on the call today, he is our Chief Commercial Officer, and he has a background in private equity and venture capital with a focus on climate tech. So the time for a disruptive technology like ours is really now. So we are experiencing the perfect storm. Climate change is recognized around the globe, and energy security is becoming the most important issue for most nations, right? And this has led to government mandates and support for renewables to replace fossil fuels. But the legacy offshore wind technologies have huge infrastructure, supply chain, and cost challenges that we'll get into in a minute. But if we look at the world at Wind Speed Atlas here, you can see that with this deep red color, how the wind resources are vast around the globe. And if you look at then the world at night, you can see where the majority of the electricity consumption is by the, it's all lit up there. And if you overlay that, the wind map on that, you can see that in very many of these occasions, it really overlaps very nicely with the population centers and where there's a lot of great usage of electricity. However, the current offshore technologies are really not viable in most of these locations due to economics and also just pure physical constraints. So if we then zoom in on the United States then and on California. So to date, the most of the focus has been really on the northeast of the United States, where if you look at the ocean depth map on the left, you see that there's very light blue color that shows that it's shallow. And that's been in the northeast, where they use fixed bottom. There is currently only 6 turbines in the United States spinning, and those are in the northeast of the US. But the West Coast has really great wind resources, world class. But this, you see here, they have very deep waters. So really the only solution here is really to use floating technology to be able to harvest that wind. So the offshore wind will play a really significant role in California's renewable energy future. And the chart on the right that I just put up shows the capacity factors of the generation during the 24-hour period. And you can see for solar, it peaks, of course, during the day. But if you look at the offshore wind, the blue line, it has a capacity factor of about 60%. And it's very steady during the day. So it really means that the offshore wind is a great complement to the already existing solar generation, and they will really help California cut the generation coming from natural gas, which is what you fire up on the shoulder in the evenings, the mornings and evenings when you don't have the solar power. So then you will be able to reduce greatly your carbon footprint as well. But let me get back to the reason why the current technologies are a challenge. If you look at the legacy offshore wind technologies, they're really based on that land style turbines that really cannot tolerate wave motions. So it's leading them to have very heavy wave resisting support structure to keep them totally steady. And that, of course, is making that, the infrastructure that's needed and all more complicated. So if you look at the other floating solutions, which on the left here, you can see that they have very deep drafts, and so they require deep water ports. And we say that also they have the iceberg effect, where more than 80% of the weight is subsurface, so they're very heavy. Ours is on the right here, and you can see that we have shallower draft, and it's a lot lighter structure. So to reach economies of scale, the industry has really made bigger and bigger wind turbines. And this chart here shows each X is an offshore wind farm. And the chart shows the evolution of the rotor diameter over time. And so by 2005, the rotor diameter was as long as the Statue of Liberty is tall. And now you have the Mingyang in China, which is 242 meters, it's planned. And that is actually, that diameter is longer than the Golden Gate Bridge is tall. So this again limits the areas that these can be deployed. And they also need specialized equipment and infrastructure. So that again limits the viable markets. So if you see the locations today that on the East Coast, so here's the North Atlantic and the South Atlantic, there are 48 spots so far that are been noted for offshore wind. If you look at the West Coast, we have 7, and that includes 2 in California. So if you want to move on to the next slide here, which talks about the latest lease auction that was done by the U.S. Bureau of Ocean Energy Management, the auction of 5 leases, and they collected from the 5 companies listed here, they're the winners, $757 million. And those are for the Humboldt and the Morro Bay, and that is covers acreage of 373,000 acres. And that has a potential for 4.6 gigawatts of wind energy, and that would power more than 1.5 million homes. But again, this is just the beginning of the offshore wind on the West Coast. You have great offshore wind resources. So, and also when you look at the number of homes along in the West Coast states, you have probably 15 to 20 million homes. So this is just the beginning. So if you look at then the topography here, they're really, and what's to come in the technology that we have today, significant port upgrades are needed for these legacy heavy and deep draft floating solutions. And you can see here that on the West Coast, you have a challenge that's different than for the East Coast, in that you have the taller mountains and you have less flat land by the ocean. So this has led to sparse land and therefore expensive coastal real estate. And also there is relatively sparse marine construction infrastructure in place already in California. So those are challenges that need to be taken into consideration, because the legacy solutions really need deep ports. They need large areas for construction, assembly, and deployment, and maintenance on the operations. And so there's significant cost challenges for the offshore wind industry. So you can see here, there's just some sample recent articles. And in the Wall Street Journal just had one a couple of days ago where they talked about this soaring cost, making it very difficult for financing for some of the developers on the East Coast at this time. So there's a need for technology and innovation to further offshore floating wind. And we have a video here and to show that how our solution really will solve many, if not most, of these challenges. And so we have this short animation movie will tell you. So we have redesigned the wind turbine, and the way that the generator and the blades are mounted is different. So those two things combined make us able to have a lighter structure. So it's held on both sides like a bicycle fork would hold the front wheel of the bike. And that allows us to have shallower draft and also lighter legs. So our solution is also wave following. So it rides on the waves and weather vanes like a ship at anchor. And that is also allowing our structure to have less tension and less stress on the anchoring system. So it can be deployed using existing boat yards and also local labor for fabrication and assembly. And it's towable to and from the site for maintenance and repairs. And here you'll see a turbine that is in need of maintenance. So it will be swapped with a fully functioning one, be towed back to shore, and will be then repaired or maintained in the port. And then it will be there as a spare, or be towed back and do another swap. This again has led us to have a lot lower O&M and capital costs, and has allowed us to allow us to unlock markets around the globe where the current technologies are really not viable today, and help us democratize offshore wind. Again, just a still of our solution. So it's scalable using this existing boat yards, and it has a simplified generator pod, lighter tower, and then much shallower draft, and it's towable. And again, it aligns like a ship at anchor. So our solution, therefore, with all of that in mind, it has the lowest offshore wind levelized cost of energy over the lifetime. And we are now having LawTech accompanied do a validation of our cost assumptions. As you can see, we're both cheaper than the floating and the fixed bottom solutions that are out there. And I just wanted to show you here, we have done successful wave tank validation in Scotland, where we had them do a test of a 1 to 60 scale. And we had wave significant heights of 17.6 meters. Right here, you're seeing just regular 12-meter waves. So this isn't that test, but we had an extreme sea state condition of over 30-meter waves, so 100-foot waves. And it performed just like we had expected and did really well in that. So we were really excited about that testing. So now we are doing a scale development plan, and we're doing the validation and testing. We're currently raising capital for our A series, and we're in the process of also finding partnerships. So we're doing validation of the design. So we've done the tank testing, which we did with funding from TechX, which is supported by Equinor, BP, and Abu Dhabi National Oil Company. And we also have a significant grant from the National Science Foundation, where we're working with NREL on the computer simulations, and also with engineering and design of our structure. So we want to build the prototype for a smaller prototype to have in the water this year, and then the larger scaled, fully functioning beta prototype to be in the water later over the next couple of years. So all in that, we see that really overcoming this climate change and energy security issues require audacious solutions. And overwhelming research or feedback that we got from research that we have done was that the current designs have great challenges, and it will be difficult to meet our goals with the current technology. And so we see the opportunity for TIO Mega being great to democratize offshore floating wind, and also becoming the dominant technology out there for floating wind. So those were my prepared remarks here and presentation, and I'm happy to have open for discussion here and hearing suggestions from everyone.
All right. Well, first off, thank you very much. Round of applause for the presentation from everyone.
Well, just great innovation. And you showed the weight of the conventional systems as being 3,000 to 4,000 tons. What's the weight of one of your units approximately, you think?
So approximately 1,000 tons for the 10 megawatts. So those are all, if you're looking at comparables, altogether 1,000 tons.
Well, that's in itself dramatic, because a lot of the cost of the wind turbine installations is just the cost of steel. So yes, you've cut the cost of steel down by 75% on something like that.
Yeah, that's correct. And yeah, that's where our savings are in that, plus not needing that specialized infrastructure to deploy.
Exactly, and you know, it's simpler. The ports are simpler, etc. Well, you haven't talked much about the generator. And the generator looks like it's an innovation as well, too. If you look at the big wind machines onshore, the ones that are on the big steel tubes, 6-inch thick steel walls, etc., they're balancing quite a bit of generator weight on the top. And it's quite long. You've used more of a pancake generator design. Tell us about the innovation in the generator.
Yeah, so we are partnering with a company we can't name right now, so we're in negotiations with them, but with redesigning the generator. So again, it's also the way that it's held, you know, between. So it's different than what you said on the others. I have my other from my days onshore wind times. I have the model here, which is held in the front, as you can see, and it's therefore needs to be totally stable, and that's why the other offshore floating wing, they have to have those very big support structures to keep them completely stable and not having the motion. So that this is the normal, you know, onshore wind type of generators and the way that's held, and then ours is held on both sides and differently. So I also have Andy on here, who's our engineer on time. If you want us to add anything, let us know, Andy, and speak up. But this is our model here. Don't know if I answered your question, Gary.
Yeah, no, that's fantastic. The other advantage that I see in the design with this four-legged structure is there is so much less strain on the bearings. First of all, you've got two bearing sets, front and back.
Yep.
And that distributes the load. And having the one main bearing on the other structure, the pinwheel on a stick.
Yes.
That has been such a source of problems with the onshore wind. That they seem to have gotten much better over time, but this just takes the problem and minimizes it, doesn't it?
Yes. So, yeah. Andy, if you want to add to this, please feel free.
Yeah, I mean, I've you know, talking with OEMs and other folks in the industry, and my own experience, you know, any engineer would support the rotor on both sides if they could. It's a far more efficient support arrangement. But because of the onshore systems yawing at the top, and, you know, needing to have a slender tower that doesn't have blade strikes when the wind changes direction and the rotor has to change its orientation, you know, that's not possible. And so the overhung rotor is the sort of Danish style architecture. But in floating, when the whole system can rotate to orient to the wind, there's this opportunity then to support it on both sides. And so we're really excited about that. Right.
And then with changing wind direction, also easy to handle. You know, the ocean is your second set of bearings there. So essentially that's what you're rotating on. That is just another key point of the innovation here. And basically, you know, offshore wind done in the traditional way, like they're doing it on the East Coast, I mean, it's just coming in at double the cost of competitors, and you're more than cutting the cost in half here. So that's huge. So what discussions have you had with any of the developers in terms of adopting this technology, especially with the 5 or so that won the lease awards?
So we have spoken with developers, and they said, if you can get this to work, this is really, really compelling, and they're very excited about the potential that we have with our technology. They're very, very excited about it. They're also seeing some of these really big challenges are in the middle of it, right? So they understand that with the cost challenges.
So the demonstration program is key to what you're going through here and getting this fully commercialized. And
yes, the validation is, and that is what we are raising our capital for right now. Although we've done quite a bit of validation already with computers, simulations, and tank testing, we really want to get ours in the water to do the testing in the ocean.
And what kind of money are you trying to raise? Oh.
So we are raising $10 to $12 million right now for a Series A.
And then the power itself, is it DC that you're collecting and you've got inversion on shore, or is it an AC generator on the machines?
We're agnostic. I mean, we can do either. I see great innovation of folks doing DC transmission, and I'm excited about it. But to us, we're kind of agnostic about that.
All right, very good. Well, Thomas, let's open up to your questions and to the audience, and I might have a few to follow up on.
I have one quick question, kind of. I mean, we've highlighted about how you showed how the shore or the shelf of California is a lot steeper than most places in the world where they've done offshore wind. I think you had for per megawatt hour, it was like $49 or something, that's 45 that you guys are hopefully getting to about.
Around 50, yes.
Yeah,
So when it gets sub 50.
Which is, I think, almost cutting current offshore wind in half, and this is floating offshore wind. So I'm excited about that. But what do you see as, I guess, the chief obstacles that you're hoping to overcome during validation?
Well, during the validations, we really want to make sure that all of course, what we were assuming with how it floats, it looks great in the wave pool. We want to make sure that it weather vanes the way that we expect it to do, and that that just that it works out in a way that we can get the capacity factor as well that we are claiming. So those are the main things that we're looking for. Of course, those are challenges, but right now our challenge is we need to raise the capital to get it in the water.
Well, capital is always the not fun part, but necessary part. So I got a question from the audience here from Jeff Bush: is how significant is the cost of utility infrastructure needed to deliver the electricity generated by the offshore wind, and anything specific to California on that?
Well, I think specific to California is going to be the port infrastructure for the regular, utility scaled offshore floating wind turbines. But for it will be the same pretty much for, well, it's much deeper off the coast of California, so the cabling and all may be more expensive there than other places, but you don't need to make it go all the way down to the sea bottom. It could be floating, subsurface, pretty deep, but still not all the way down to the sea bottom. I think that's a significant cost for all of us. I had it, if I may show you can see the percentages pretty much in the graph that I have in here. I'll share that one more time to get back to let's see, the cost estimate. So, oops, here, can you see my screen?
Yes.
So the blue part is really the electrical infrastructure cost. So you can see that it's higher for the floating because you also have to have a flexible cable, whereas the fixed bottom, there's less cost. But here you can see the percentages of what that is of the total cost for the utility and the electrical infrastructure setup.
And a follow-up on that is who's primarily going to be responsible for being able to finance that? The wind developer, the leaseholder, the local utility? Do you know where they're talking about, or who's going to be financing to build that infrastructure?
See, I don't know exactly how that will be split up, but I would imagine that the transmission piece is going to be with the utility build out. Whoever's the transmission, the company that is doing the transmission in the state.
All right. Then I'm going to call on Peter Mackin, who always has his hand up.
But everybody has great questions, so let's see what Peter has.
Well,
okay, yeah, just to get to that question you were asking about who builds the transmission infrastructure. It's unfortunately it's always the developer. So it's not the utility. Sometimes the ISO will have transmission plans. They'll basically forecast resource development areas, and they might fund transmission to be paid for by ratepayers out to bring in the resources, but not always. So on the initial cut, when somebody first comes in and says, okay, I want to connect to the grid and I want to connect, say, to Diablo Canyon or Morro Bay offshore, they're going to pay the full freight for the interconnection. At least that's what they're gonna have to put deposits down based on that cost. And then they may save, they may not have to end up paying it in the end, but initially they need to have the financial wherewithal to cover those deposits from the beginning. So Yeah, and the other thing is, it's more than I got more comments than questions. You know, I don't want to be a Debbie Downer, but transmission offshore on those two resource areas that were shown, the Morro Bay Diablo Canyon and also the Eureka one, it's awful. There basically is no transmission. So I mean, there is transmission around Diablo Canyon, but it's already taken. Other developers have already claimed it. So, you know, it's you're going to need more. So it's going to be expensive and time consuming. So we'll see what happens. But I do want to say that this design that you've shown, I think is brilliant. It's it's a heck of a lot. It's ingenious compared to the other stuff that I've seen. But I do have a question. So my question is, well, two questions really quick. Where are all the auxiliaries located? You know, like in a traditional wind turbine, they're up in the nacelle, you know, the pumps, the cooling, transformer, et cetera. It's all up there. So where would those things be located in your design? And then the second question is, on that video that you showed, basically replacing a a turbine that was dead with a new one. How do you actually, where do you make the interconnection to the grid? Because is that going to be underwater at the pivot point, or is it going to be someplace else?
Yeah, should I? So for the first question, all of the auxiliary equipment right now. So in our current kind of nacelle arrangement, there isn't the space for it. So it's still an open question that we're debating with this OEM partner that Brita mentioned, about whether there'll be some sort of external housing up at hub height, or if we can get it down closer to sea level, which has the nice benefit of lowering our center of gravity. So where that is still an open question, and there's sort of pluses and minuses on both sides of that. The switchgear for the electrical connection, we want it above the water, so it's going to be just above that hitch point that you can see there. So where those mooring standoffs connect, it'll be just above there on a platform, so we can get the switchgear out of the water.
Okay. Oh, okay. So if you have to do a change out, you're going to basically disconnect there at the triangle that's sticking out from the wind
Right
turbine
here.
there.
Yeah.
Okay. Okay.
I don't know if you can see my cursor on there.
Yeah. Perfect. Okay. Great. All right. Thanks. Yeah, I think that's, well, I don't want to hog the conversation, so I'll let someone else ask questions now. Thank you very much.
I do want to note on the transmission part, the CEC and the CPUC for the past, I don't know, 2 years ago, they started looking at how to get transmission out to those areas, and are actually looking at building 2 transmission lines, one from the south up and then one across like they have before. So at least they're started on making that planning and dealing with the obstacles around it. And they're
Yes.
Yeah.
Those are billion-dollar transmission projects, but yes, somebody's going to pay for them. We just don't know who yet. Well, I guess I take that back. The ratepayers always pay. So.
Yeah, I'm going to call on Jeff Bush because I tried to read his question earlier that he put into the chat to me. So, Jeff.
Yeah, Thomas, thanks for your comment on the transmission lines. And Peter, you did a great job of asking many of my follow-up questions. But I'm just curious, from the background that you all have in the wind world, and Gary, your background with Northeast Utilities, how does the power get distributed once it gets on shore? I mean, if you assume that a transmission line magically appears and brings the power on shore, is the utility grids, do they have to undergo significant improvements to distribute that power to all of their customers throughout their service territory? That was my first question. The second question is kind of off the wall, but we have a number of offshore oil platforms in Southern California, many of which may not have any use going forward as we transition away from fossil fuels. And I'm just wondering if there's any benefit of co-locating some of these offshore wind resources with those platforms, even if they're smaller scale, but if nothing else, to get 5-10 megawatts in locations by those platforms.
Well, let me comment on that, Jeff. You may or may not remember that El Paso had a number of deep offshore platforms in the production company that then got sold off. There's a lot of safety issues, even on a platform that's not in use. I just wonder about, maybe you could put some transmission equipment on it, but I think it'd be really difficult to get clearance to put like wind towers on those old platforms, given some of the other things that they're connected to, because they still have the wells and everything coming up. So I might not be too optimistic on that. Plus, they're hard to get onto and off of. Whereas, towing this thing out and replacing it, it's like changing a light bulb. That's one of the advantages I see on that. But see if anybody else has any comment on the use of offshore platforms.
Well, this is Peter. I mean, first off, I think most of the platforms are in state water. They're close to shore.
Yeah, true.
So the biggest problem you're going to have is if you try to mount wind turbines on those platforms, they're going to change the visual impact, and that, I mean, it may be allowed, but you're probably going to get complaints from the people near shore that can see it. And that's the reason for the floating offshore wind, is that you tow it out, like 30 miles offshore where people can't see it, and then it's like out of sight, out of mind. But then the continental shelf drops off really fast, so you end up. That's why you have to go to floating, because it's so deep out there. The other thing I would say is that the platforms do have power supply, but it's usually not huge. It's probably enough for maybe a couple megawatt or so of wind turbine. You'd have to upgrade it if you added more, a lot of wind turbines to it. Plus, then the shore connection might be not have the capacity for it. So there'd be significant upgrades probably needed if you wanted to add, multi-megawatt wind turbine to a platform. But it's a good idea. It's something that could be explored. But I think the things that Gary mentioned and the stuff that I was just talking about, you're gonna have to take that into account. So,
All right.
How about the conflicts with shipping and fishing of putting these things out even 12, 30 miles offshore? Have you done any studies on resolving those conflicts?
So as a start, we have focused on our technology, but we do not want to overlook this. This is very important so we would really welcome anyone to partner with us on looking at those impacts. The one thing that I can say is that ours can be towed and moved if that is needed over time, right? So that is one of the advantages of our solution. But we definitely, this is something that's very important, and that we want to make sure that we participate in that discussion.
Okay.
And the analysis that needs to be done on that. Yeah.
I want to quickly actually kind of expand on, at least on the switching of platforms versus doing maintenance on them. A question from Ed, and then we'll get to Peter Bell's question. So he says, could you talk more about the process of switching the platforms versus doing maintenance like on traditional floating platforms?
So the one thing that's good, and I'll let Andy also comment on this, but we don't intend to have anyone on ever really board our turbine offshore. So it will be robotically changed, right, and switched and then brought into shore, and that's where any of the work will be done. So that takes away a lot of that human risk also, and safety. So we don't intend to do any work offshore, and even to board the platform offshore.
All right, Peter, you have your hand up.
Yeah, a couple of questions for Brita. I'm just curious about energy storage at the side of the windmill. And have you ever done any discussions with someone like an MROD or someone like Greg Kushner, who runs MROD, doing the wireless transmission? Because that was one of their original use cases for wireless power transmission, was to allow your kind of technology to bring the power back on shore. And so I'm just curious about what your thoughts on energy storage at the windmill is, so you can balance out the power, and then also wireless transmission inbound.
Yeah, so the energy storage, we have not looked at it for storing electricity offshore, but we have one of our members of our team is really looking into green hydrogen too. And that could be, of course, stored offshore. But right now we're focused, just to solve and get our technology to work. Andy, have you done anything else on the storage that I may not be?
I mean, I'm fascinated at the possibilities of it. Liquid fuels, compressed air stored underneath. There's so many opportunities if you can store locally. But like Brita said, we're focusing on our current scope, and so we haven't explored it deeply.
Well, let me just throw in a question here. There's a company in France that's called Eolind. Their device looks very similar to yours. Do they also have access to the Northeastern patents? Is there any shared DNA between your two companies?
There's no shared DNA between our companies, and they don't have. We don't have access to each other's patents. So that's different. So they're different. They have a lot greater weight underwater, and yeah, we don't share any of the patents.
Yeah, they have a more conventional generator too. All right, let's go on, Thomas.
All right, we're going to try to wrap it up with just one or two more questions. Jeff, do you have another one?
Well, I just sent a note to Peter. It was really just a comment more than a question. Is that, I hear all this on the offshore platforms. That's not apparently a viable solution for building 10 megawatts or more of generation. But I'm wondering, since building transmission is so difficult, especially in this case, or really any case in California, maybe to benefit from the infrastructure for purposes of developing a pilot generator, meaning a generator that might be a megawatt or less. Maybe this would be a spot to do some testing. Because what I'm concerned about is the technology might actually leap ahead of our ability to actually receive the power.
Yeah, and we have our argument is also that we believe that bigger is not necessarily better. So as you're getting these larger and larger structure, they become more and more complicated to deploy, right? To fabricate and launch from shore too. So we don't believe it's going to go beyond 10 megawatts. We think it's going to be the optimal economics are going to be sub 10 megawatts.
All
So
right.
just to comment on that, Jeff, I'm looking at the screen. I'm probably the only one old enough to remember that there used to be a nuclear power plant in Humboldt Bay. And there's a big transmission line out there. The Humboldt power station was like 65 megawatts.
It's wasted.
Wow, I did not recall that. I remember Peter's point and a few other offshore platforms that are probably long gone, but I did not remember Humboldt Bay.
Yeah, so there has been load growth in the Humboldt area, so it doesn't have to transmit too far, but there's actually a nice corridor back to the Pacific Intertie from Humboldt. So it might be one of the best places to go. So just
well, yeah, Gary, this is Peter, but the lines that go there are only 115 kV, so they're only good for a couple 100 megawatt max.
That is true, but there's a corridor.
Yeah, yeah, there is. I mean, and it goes through forest too, so it's subject to a lot of outages, but yes.
We'll talk about that some more, but there was a program created called the Northern California Transmission System. It upgraded a much lower voltage line to a much higher voltage line, and it was quite inexpensive. So at any rate,
yeah,
minor point, but Humboldt might have a favored position just because of that transmission corridor.
I get a kick that we want to go offshore to generate wind because there's a lot of land use issues in California where people fight over the use of land. And here we are with this huge opportunity to build wind off there. And now land use is like, well, what about the cable?
Yeah, exactly.
All right. I'm going to toss it for the final comment back to Brita. If there's anything you want to wrap it up with.
No, I think I would like to wrap it up with that. As you said, Thomas, the offshore wind resource off the coast of California is enormous, and it should be able to power more than multiple times over the consumption. And again, there are of course challenges that all of the questions we got to about transmission, the port infrastructure, and all that needs to be overcome. But I am very, very excited about the prospects for California. It should be able to become energy independent. So that we're excited to take part in this build out in California, and looking for, of course, partners and investors. So really excited to hear from all these good questions, and also hear from people that want to partner and invest.